We saw in the previous video that with an isothermal expansion, for the reversible process, the heat that's put into the system is completely turned into work. And for the irreversible process, only some of that heat is turned into work. The other portion of that energy is lost as heat. And so here, we want to develop more rigorously the differences between the reversible and irreversible heat engines, and then kind of develop an equation that relates the two together. Okay, and so once again we have the same diagram for the isothermal expansion, and we saw that for a reversible heat engine or reversible isothermal expansion, we saw that the dq reversible was equal to dw reversible, and that was just equal to pressure of the gas times dV. Okay. For the irreversible isothermal expansion, our dqIRR was equal to the negative of dwIRR, and we know that's just equal to the pressure at state 2 times dV. Okay? Now for the reversible case, the pressure of the gas, in that reversible case, the volume is going to be changing so slowly that the pressure of the gas is also going to be changing very slowly. And it's going to range from P1 and then decrease all the way down to P2. All right? And so, in general, if we relate P gas for the reversible case to the P2 in the irreversible case, P gas is going to be either greater than or equal to P2. Right? That's the relationship between the two. Right? And then similarly, if P gas is going to be greater than P2 and dV is just going to be the same, that means that also, if we take these same equations, P gas is greater than P2, that means that dq rev is going to be greater than or equal to dqIR. Okay? So that's the relationship between the two dq's that we get from the energy balances. What we're going to do next is we're going to divide both sides by the temperature of the process. Okay? And in our case, for this isothermal expansion, it's the same for the reversible case and irreversible case. So we have dq rev divided by T is greater than or equal than dqIRR divided by T. Now this ratio we have here of dq rev over temperature, we're going to give this a new variable name. We're going to call this ds, where this S stands for entropy. Right? And so essentially what we have here is that the derivative of entropy is equal to the derivative of Q reversible divided by temperature. And this ds is going to be greater than or equal to dq irreversible divided by temperature. Right? And so since we have these differentials on each side, what we could do is then integrate. And so if we take the integral from S1 to S2 of ds, this will just give us S2 minus S1, which we could call a delta S. And so our change in entropy is going to be equal to the integral of dq rev over T. And this is going to be greater than or equal to the integral of dq IRR over t. All right? And this equation that I just wrote out here this is known as the second law of thermodynamics. So I've now introduced to you the second law of thermodynamics, but right now, to be honest, it's probably just a math equation to you, right? And it's I kind of just introduced a variable out of nowhere. And so what I want to do now is let's take this equation and let's kind of break it down term by term. All right, so let's break down second law term by term. All right, and so the first thing I want to talk about is that dq rev, And so this dq rev, you could think of this as the incremental amount of heat required for that reversible process to occur. Okay? Right? And the way we determine dq rev is from the energy balance on our system, specifically for that reversible process. Okay? And so, for instance, when we were dealing with an isothermal expansion, we see that dq rev is equal to the negative of dw reversible, which is just p gas dv. Okay? So that's specifically for the isothermal expansion. Okay? The T that dq rev is divided by, that's going to be the temperature of the system boundary in which that q rev enters in. So temp of the system boundary okay? And if we think of that isothermal expansion again, this system is a little bit easier to understand because the temperature is the same all throughout the system. Okay? Now, whenever we take the integral of dq rev over t, remember this is dq on top and then just temperature on the bottom, not d temperature. Okay? So when we take the integral of dq rev over t, the answer we're going to get depends on whatever the relationship between dq rev and temperature is. Okay? And so for example, if I go back to the isothermal expansion, I have dq rev here divided by t, right? Temperature, it's isothermal, temperature is going to be constant, so I could pull it outside of that integral. And then I know that dq rev for the reversible isothermal expansion is equal to just p gas dv. And so our integral is going to go from volume 1 to volume 2. And if I assume that the gas is an ideal gas, so we could apply the Ig law, and we get nRT dV over V. This temperature is still a constant, and in fact, we could pull it out of the integral, and we could cancel it out with that temperature in the denominator. And so what we're going to get in the end is that this is equal to nR natural log of volume 2 over volume 1. Okay? And I said here that this integral from the second law of thermodynamics, this is going to be defined as the change in entropy of our system. And so this entropy we're looking at, this delta S, if we go through the units of nR natural log of V2 over V1, what we would have are units of energy over temperature. Okay? And so that's the first law of, or the first term in that second law of thermodynamics that we're dealing with. If we go back here, we're also see that on the right-hand side of the equation we have this weird inequality that we're dealing with, right? And so what we could do, rather than dealing with an inequality sign, we could rewrite the second law in this way. So delta S is equal to the integral of dq rev over t, but instead of an inequality, we could write that the right-hand side is then going to be equal to the integral of dq IRR over t plus some term called Sgen, which is the accounts for the entropy generated by the process, where Sgen can be one of three things. Sgen can be greater than 0 if we're dealing with an irreversible process. It could be equal to 0 if we're dealing with a reversible process. And it could only be negative if we're dealing with a process that is physically impossible. All right? So this is, it may be a more formal way of writing the second law of thermodynamics.